your computer muted. Please, with this many people, please try to keep your computer muted while the others are speaking. And then if you have questions, you can use the raise hand feature. But we'll try to reserve a good portion of time at the end for to really get in with discussion and questions. But to remind everybody why we're here, the legislation, North Carolina General Assembly passed legislation in 2020, which required the department to develop new transport zones and delivery factors for the Neuse watershed. And so that's what is driving this entire process. Again, this is really a focus on delivery factors in the watershed. So with that, Respect has the consultant that has been working tirelessly to get us products to use to develop these transport factors. And I will let them introduce themselves and take it away.
All right. Thanks, Pam. I'm going to share my screen. Hold on one second. Making sure I get the right one. All right.
Looks good.
Looks good. All right, so yeah, the agenda's already been kind of on the screen, but we'll briefly go through some model development. We spent quite a bit of time last stakeholder meeting on that, so I'll just kind of touch on that again, get a review, and then really dive into some of the calibration and validation results and kind of end our discussion before we pass it back to Pam on the delivery factors and how we develop those. I'll just briefly introduce our team. Our principal in charge was Russell. He's also the W&R Senior Vice President at Respec. Seth Kenner was our project manager, and he's also the developer of the scenario application manager, SAM. And then we have Paul Duda, who's the QA QC officer, and then Cindy and myself did a lot of the modeling, development, and calibration. So the model we used for this was the hydrologic simulation program, Fortran. It's been in use probably over 50 years now, core model in the EPA basins and Army Corps watershed modeling system. With this, we can do continuous hourly simulations representing multi-land use watersheds. And it works for multiple pollutants, like there's all your eutrophication ones, and then you can also do even more with bacteria and metals. Can represent surface and subsurface and stream flow, and then all the hydrology and water quality processes, including point sources. So this is just kind of a schematic we like to show that kind of shows how HSPF works. Kind of start by with your forcing data, so all of our meteorological records, those get applied to our different model land covers, soils, and subwatersheds within our basin. And then it simulates overland and subsurface flows to a receiving reach. And in there we have our nutrient cycling, all of our hydraulics and fate and transport to carry it through the system. And within the model, there's a lot of control you can have with the model parameterization. And that really kind of governs what each one of these land uses kind of carries to a stream. So there's quite a bit of data that goes into this. I won't read through all of these, but we have our meteorological records. That's kind of upfront, along with our point sources and water use. Then on the back end, we have our stream flow and water quality data to help us calibrate. And then a lot of this other stuff over here is a lot of geospatial and other types of data that help us characterize and segment the model. So usually start with our subwatershed delineation. We did include a boundary condition at Falls Lake, and then we broke our basin up into subwatersheds. At most Tuck 12 outlets, and then any applicable impairment outlets, monitoring sites and modeled lakes. We use NHD version 2 with their flow accumulation grid and direction grid, along with the ARC GIS hydrology tool set to actually do our delineation. We ended up with 231 subwatersheds with an average size of about 21 square miles. And then each subwatershed gets one receiving reach. So for our reaches, we modeled seven of them as lakes or reservoirs. One of those was impaired for an applicable constituent, and then the others we just kind of selected ones that are connected and over 200 acres. This table over here is kind of a summary of those lakes that we represented explicitly in the model. So that left 237 streams or rivers, and we used the high-res flow lines to kind of develop those spatially. And then for HSPF calculations, we got our length, slope, and elevation. And then each one of these reaches needs what's called an F table or function table. It's basically an extended rating curve. It kind of tells the model you have this much volume in the reach, so this is what the outflow is going to be. So it's set up so at a range of depths, we have a surface area, volume, and flow. For lakes, we use some other additional outflow information. And for the reaches, depended heavily on cross sections. And there was a lot of HEC-RAS work or HEC-RAS modeled in the watershed. Basically, all of our main reaches had a HEC-RAS where we could extract those cross sections to help develop our F tables. For the meteorological data, we used the gridded products Prism and NLDAS. Prism is a kind of higher spatially resolution data, but it is only at a daily time step. So we use Prism for precipitation, and then NLDAS for basically our other time series like temperature, evaporation. And then with this, we kind of define our MET zones, which are our subwatersheds that share the same precipitation time series. And this is important because land uses in these zones share the same parameter sets. So the steps for this process, we obtain the precipitation for our subwatersheds and then produce correlation and adjacency matrices to kind of understand how well each subwatershed's precipitation totals are correlated, and then we can aggregate from there and then export the data to a watershed management data file to be input into the model. Other time series that we needed to fill or process include our atmospheric deposition, so converting those weekly or monthly products to a daily time step. Kind of the same thing for water use data, so surface and groundwater time series were filled with monthly averages. And then some of our calibration data, so our stream flow and water quality samples, we needed to do some conditioning of that to be able to use it. And then finally, the other major input are the point sources. So we filled these missing data, had to do a lot of kind of processing with this. So we fill our missing constituents using default concentrations. If it was completely missing, otherwise we interpolated. If it was a small data gap, then we moved on to filling with monthly averages and then filled with an overall average. And this is kind of the table we used for the missing constituents and kind of based the concentrations of nutrients, BOD, and sediment based on the type of facility. The next step in the process is our schematic development. So really kind of defining our land segments that we're going to represent. So we started with the National Land Cover data set. And here's kind of the distribution of land cover in the watershed. Kind of pretty even mix of cropland, wetland, and forest. And then the next major category would be developed areas. We also looked at hydrologic soil group, different crop types, since this was a large portion, kind of seeing what the main crops are in the watershed, pretty much dominated by soybeans, corn, and then the double crop. And then, a few specialty crops mixed in there. I looked at tile drainage and then manured versus unmanured areas to kind of get our base land use stuff. And I think in the next slide, I have a schematic that shows that, but we also represented our MS4 areas, kind of used the same land uses, but just kind of gave it a special number to track it differently in the model for permitting purposes. And we did represent septic systems using census block pop data outside of sewered areas. So this flow chart just kind of shows how we aggregated and kind of arrived at our final pervious and impervious classifications in the model. So starting with our NLCD types, we kind of aggregate those into a model land use and then use other data to kind of parse that back out. So like, for example, with the developed areas, we got percent impervious for our EIA calculations. And then the cropland, using crop types, looking at soils for drained and undrained, and then also looked at some Chesapeake Bay kind of estimates to define what is likely manured versus unmanured grain. So then putting this all together, we kind of stack all of this analysis and then produce our schematic. And this really links all of our source areas to a reach. So the final step in development is just parameterizing the model and get it running. So we leaned on past efforts that we've worked on in the eastern United States, so Rhode Island, Connecticut, and Pennsylvania. Then there's some additional data we get from GIS for parameters too, like slope, elevation, and some other soil properties. So that was the development kind of in a nutshell. So we'll move on to calibration and validation. So calibration is really just adjusting parameters through an iterative process until we get some resulting predictions that provide a good correlation with the observed data. Then validation is really a test on the test of the calibration on a separate time period to kind of build better confidence in the model. The modeling period for this project was 2004 through 2022. We did simulate 2003 as kind of a warm-up period to help balance storages in the model. We chose this period because it kind of captures the driest and wettest year in the last 30 years or so. So we kind of set some calibration criteria. So we need to kind of set some limits on how good is good enough. So here's a table of kind of showing what would be considered very good, good, or fair based on the parameter we're looking at. And then also, looking at some model fit statistics for our flow calibration, based on the R and R squared and Nash-Sutcliffe. And then, along with these criteria and some others that aren't on here, we also based the criteria on our site classification. So our primary, secondary versus tertiary sites. And just to note that we excluded the major hurricanes from our statistical analysis. So for hydrology, here's kind of a map of our calibration sites. So we have a boundary condition at Falls Lake, and then we had 5 primary hydrology sites. So these were on the main stem of the Neuse that had a full period of record, and then also one on the Contentnia Creek. Secondary sites were kind of on relatively smaller drainages with a full or nearly full period of record. And then the tertiary sites, usually really small drainage areas or a shorter period of record. So for the hydrology calibration, kind of four main components, and then it's an iterative process. So we kind of go through this multiple times, but first we establish an annual water balance, adjust low flow and high flow distributions. Then we look at our storm flow and hydrograph shape and make seasonal adjustments. So these are kind of the main plots we look at, kind of our qualitative analysis. And in most of these plots, I'd say all plots, if I say otherwise, we have our observed data are in blue and then our simulated data are in red. So here's our annual runoff at our main downstream gauge on the Neuse. You can see the model, does well at representing, the dry and wet years. Overall average is really good. We see the model capturing the kind of seasonality of runoff. Here's our flow distribution or flow duration curve. We're kind of capturing all the range of data, under simulating a little bit. It's like 10% of the lowest values are a little under simulated. And then here's just kind of a subset, looks like year 2019 of just our kind of annual hydrograph time series. So looking at all of these plots along with all of our statistics, using qualitative and quantitative metrics to arrive at kind of the best calibration we can. So here's a look at the final hydrology calibration statistics. And so I have each one of our gauges, the segment name, drainage area, kind of percent of the data that were available, and then the calibration type. We have our primary, secondary, and tertiary gauges. Then looking at our monthly and daily R squared and model fit efficiency, which is the Nash-Sutcliffe. The math is the same. And then storm differences, we look at kind of our percent difference in volume and peak flows, and then just an overall total volume difference. So the model does really well with the primary calibration gauges. And mostly it ranks very good. Secondary gauges kind of rank from fair to very good. And this is meeting the criteria that we set forth in the report in QAP. And then our tertiary gauges, overall, I think a pretty good representation. Some of these really poor performing ones are mostly driven by, we only had a year of data to work with, and it's a really small drainage area. For the validation, we kind of did what's called a split sample validation. So we kind of did a subset of the full calibration period, looking at a dry 5-year period and a wet 5-year period. I think this should be 2007, so that's a typo. And then kind of look at all the same statistics, and I just kind of grouped them here. It's a little easier to look at. And looking at it two different ways. So area weighted versus just a true average of the same statistics of the last slide. And overall, the model performs better during wetter years. Kind of a really very good calibration when we look at it area weighted. In the drier years, we are over simulating slightly our storm volume and peaks, and then that kind of causes an overall somewhat higher overestimating our total volume. So then these are just kind of both of our validation periods. You can see here's the drier area. We're over simulating a little bit on our peaks. We still get a really good response in the model following kind of the rising and falling limbs. And here too, upper 5% or so over simulating that. The wetter period is a lot better, maybe slightly under simulating some of these peaks. And then, this is where we see kind of the, 5% under simulating those base flows, kind of these really low flow periods. We also looked at snowfall and snow depth using SNODAS gridded data. So this is showing a map of snowfall and water equivalents. And then on the right, just kind of bar charts of comparing our observed snowfall and snow depth and water equivalents. And we see that the model captures pretty well that kind of northwest to southeast gradient we see in the watershed. So overall, the model's doing pretty good with those. On average, the snowfall only accounts for about 1% of the total precipitation. So we didn't spend a whole lot of time, but it's good to make sure that that's well represented. And the last thing in the hydrology that I'll talk to is just looking at water balance results. So comparing two independent studies in the region to our HSPF results. So we looked at the Cape Fear SWAT model and then the 2009 basin plan. They kind of broke out the two main ecoregions, Piedmont and Coastal Plain, and then just plotted the HSPF results next to them, and all of them kind of look pretty similar. So that provides pretty good justification and for our parameter set. And we also looked at the water balance by land use to ensure our kind of by land use the results make sense. Well, on to the water quality, and we kind of did the same sort of grouping of our sites into primary, secondary, and tertiary locations. We have 3 primary water quality sites. These had the most samples, and they were downstream on major drainages. So we have one at the Neuse, kind of above the confluence with the Contenia, and then one on the Contenia, and then on the Neuse again downstream of the confluence. Secondary sites had greater than 1,000 samples, and these were on key areas like model lakes and kind of somewhat substantial drainage areas. And then our tertiary locations generally already covered by an upstream secondary location, or I mean a downstream secondary location. And we really only reviewed these when we were having kind of inconsistencies within kind of a drainage basin. And then some samples we couldn't use because they were on an estuary or there really weren't a whole lot of data to deal with. So the calibration process for water quality, first we estimate land use specific parameters. Then we compare our simulated loading rates with expected ranges and adjust if necessary, all the while kind of reviewing and calibrating our in-stream parameters to observe data. So the table down below, that's in the report. I'll kind of show these values graphically in a few slides. But we compared the HSPF results to the Chesapeake Bay program loading rates in an area that was kind of closest to the Neuse and use that as a comparison. So for the water quality data, we did remove our non-detects from our statistical calculations. We don't know if it's 1 or 99% of the detection limit, and mainly because we had a large enough sample size to work with to where we didn't really need to make assumptions on those non-detect samples. We did include them in the plots just to kind of visually check and try to get the model below those. For the water quality calibration, we looked at TSS, DO, temperature, total phosphorus, and then our different nitrogen species, so nitrate, ammonia, ammonium, and TKN, and also looking at chlorophyll A. So these plots on the right are just kind of examples. I'll get into more later on too. But we kind of look at our daily time series, monthly box plots, and then concentration duration curves. And again, like hydrology, all the simulated is in red and observed are in blue. So now looking at kind of land contribution results, we'll start with sediment. And this bar chart on the left just kind of shows our sediment loading rate in pounds per acre, and then grouped by kind of aggregated model land class. And then these red lines across are kind of the ranges of the Chesapeake Bay data. And the arrow just means it goes way above the max value here, but overall, we kind of follow the Chesapeake Bay loading rate patterns. The biggest discrepancy in the sediment is our pasture hay and our grassland. They seem like they're kind of flip-flopped. And we think maybe that's due to differences in slope or soil erodibility when compared to the Chesapeake Bay results, because their overall kind of larger data set is more in line with what we have here, with pasture and hay being higher than grassland. With kind of the land use calibration too, we also look at kind of our allocation, source allocation pie charts, and we look at those in relation to total runoff. So these are basically saying the total load from the source or land use that makes its way to the nearest reach all across the basin. So for sediment, we have the runoff from our developed categories, and agriculture is about 50% when we look at a runoff. When we look at total sediment, it's more like 60 to 75% from those sources. And then we also include kind of the bed and bank portion, which is our in-stream scour. That's a daily net positive removal of sediment to a downstream reach. This is never negative, so if we do have deposition occurring, the land sources upstream of that are reduced relatively based on kind of the current load distribution. So it's saying kind of all the sources in the watershed, we get about 16% from scouring of the sediment bed. We do include these for total nitrogen and total phosphorus, a bed bank proportion, and that's mainly due to the adsorption and desorption processes of those nutrients on the sediment. And these end up generally being a lot smaller because we have more pathways for loss with nutrients other than just settling. So now kind of the same results, but now we're looking at nitrogen. So again, the same sort of bar chart on the left, and then also a map of subwatershed loading rates. So again, nitrogen does a really good job at following kind of Chesapeake Bay patterns and ranges. We're slightly up, a little bit lower than the soybean range and grassland range, but these are really tight. So that could just be due to differences in climate, soil, and topography. Here's the source allocations for nitrogen. Kind of going through the same process. Our developed agriculture categories account for 60% or so of the total load, and then a lot less relative to runoff for our more natural land uses. Point sources altogether account for about 8% of that source, or I guess of the total nitrogen load. And then finally for phosphorus, again, same thing where we're following the trends. I guess the HSPF trends kind of match the Chesapeake Bay trends. For our manured grain, we're slightly outside of the Chesapeake Bay range. And I think this goes back to our nutrient application inputs that we used, where cropland has about 10 times the amount of application than our developed turf grass area. So it's driving that. And then source allocation again, pretty similar to nitrogen, but a bit larger from the point source's source. So moving on to our water quality kind of in-stream calibration. Here's the final statistics for the model. So we have all of our individual constituents that we calibrated, and then just grouping the results. So here is all together. We have our observed concentration versus our average simulated concentration and percent difference. And then just kind of looking at the three main primary calibration reaches too. Overall, everything is considered very good according to the criteria, except for slightly overestimating sediment in our downstream primary reaches, and then way overestimating chlorophyll A in our primary reaches as well. And I say way overestimating, it's kind of a far stretch where, if you look at the averages, it's 2 micrograms per liter difference there. So I'll kind of go through all of these pretty quickly and then just kind of touch on, some of these different discrepancies that we see. So calibration usually begins with sediment and temperature because a lot of processes are temperature dependent. We also have nitrogen and phosphorus associated sediment. So the temperature is very good calibration, which is usually the case. There's very limited parameters that you can calibrate with, and it's really driven by our solar radiation time series. So if that's good and correctly applied, usually temperature falls into place relatively easily. And some plots I'll be showing too for the other constituents as well are called longitudinal box plots. And it really just kind of, we get a snapshot of the ranges and trends across the entire watershed. So we're looking kind of from upstream all the way to downstream from left to right. And here's just the reach numbers. So if it's an even number, that denotes that it's a lake. If it ends in 0, that's on the Neuse main stem. And then kind of this block here from like 544 to 595, that's the Contentnia drainage. And overall temperature, looks good across the watershed. We get higher temperatures in the lakes. So for sediment, like I said, we're kind of under simulating overall, and you can see it in the longitudinal plot, kind of under simulating mostly in the upper part of the watershed, and then over simulating downstream on our main downstream gauge and Contentnia. But it does capture kind of the spatial trends in the watershed pretty well. And our lake, let's see, yeah, our lakes could be improved if we include a proxy for VSS in the as a component of TSS. HSPF just simulates the kind of inorganic component of TSS. So I'm just going to show quickly kind of the discrepancy driven by Contentnia Creek. So this is showing the concentration duration curve for the Neuse upstream of the confluence, and it's a really good kind of fit there. But then we go to the Contentnia and we're over simulating kind of the upper quartile. And we did some tests to try to see if we could lower that, but then we would need kind of an unrealistic amount of scour across the entire other parts of the watershed to kind of make up that difference from the wash off. But that's really driving kind of the slight overestimation on the downstream part of the Neuse. On to dissolved oxygen. Calibration for this really focused on kind of the lower areas. This is where you have your problems with aquatic life. So that's where the calibration focused. Across the watershed, again, it represents it fairly well, except in this lake right here, consistently under simulating by about 2 milligrams per liter. And this kind of had a small sample size relative to everything else for DO. And there are some, excuse me, some model limitations with lake simulations. This model simulates a completely mixed system. And we know that lakes can stratify and one area could be different from another. So on to the total nitrogen. So the total nitrogen breakdown based on the observed data was about 43% nitrite and 57% TKN. 10% of that TKN is in the form of ammonium. So for the inorganic nitrogen, so our nitrate and total ammonia tend to slightly over-simulate it. This is showing nitrate right now, and kind of just a few gauges where we're actually really over-simulating, and those are pretty driven by point source inputs. So we spent some time reviewing those, and all of those, matched the data records pretty well, so nothing we could really do there. So here now we're showing ammonia, and that's over-simulated kind of across the watershed just slightly. And these were pretty sensitive to our septic system estimates. So in the colder months, we were kind of unable to cycle those. So this is an example for monthly bar chart or monthly box plot for total ammonia. You can see, during the regular growing season, the model's representing it pretty well, but just in these colder months, kind of over simulating. TKN was slightly under simulated overall, mostly driven by kind of the lake concentrations. Again, with those model limitations, it's kind of hard to maintain that much phytoplankton growth to keep this elevated. But I mean, overall, the rest of it looks really good. So then putting those all together, we get total nitrogen and well represented longitudinally. Really captures kind of the differences we see across the watershed. Does well seasonally. This is total nitrogen. It doesn't look like there's a seasonal signature here, but then we, look into the components of TN. We're capturing the seasonality of TKN and the seasonality of nitrite. We also represent it pretty well as a function of flow. So here's another type of plot we tend to look at. It just pairs the observed and simulated data, but as a function of our flow. And you can see the model kind of stays within, for the most part, those ranges of the observed data. So for the total phosphorus calibration, showing the time series plot here, and the model captures the ranges pretty well. Here's the concentration duration curve. The seasonality model does really well at that too. And then, well represented watershed wide, again, picking up on all these differences and trends. We had 2 locations where we were pretty off, and some tests indicated that it might be kind of some agricultural processes driving those differences, but we didn't really have much justification to really crank those parameters on those specific land uses. So we just kind of left it like that. And these are really, rest of it's really driven by point source inputs, the concentrations are. So if I'm just going to cycle through back and forth, this is the same exact plot, but with the point sources turned off. Then finally, the chlorophyll A calibration, we really only had 9 out of our 27 sites that had usable data. Didn't have any usable data on tributaries, so we have, 5 pretty good lake sets, and then 4 on the, um, I guess 3 on the Neuse and 1 on the Contentnia. So the model does pretty good at capturing the large differences between the lakes and just the reaches. And we did see some pretty big seasonal differences between lakes and rivers. So we're getting the seasonal differences or the seasonal concentrations pretty good for the lakes. Um, but for the actual streams and rivers, um, we're not really hitting the seasonality, and this again comes to kind of the limitations of the model with the nutrient dynamics and HSPF. You really only get one phytoplankton class to represent all the phytoplankton. Um, given the differences between these, there's probably different types of algae in lakes versus rivers and so on. The weight of evidence approach concluded that the model met performance criteria and is an acceptable representation of the Neuse River watershed. Looking at all of our different things, our rates, source allocations, mean differences, and then all of our different types of plots. And just to note that a summary of all this assumptions and model limitations are provided in the report, kind of at the end of the calibration section. Finally, we'll talk about delivery factors using SAM. So the Scenario Application Manager is a standalone program with GIS mapping capabilities. No HSPF modeling experience is required, but SAM does require a calibrated HSPF model and just GIS watersheds to kind of link locations to the model. So it's used in this case, to develop our transport delivery factors. You can also do a lot of different existing condition analysis and kind of an infinite number of what if scenarios. So I'll just kind of give a quick overview of some of the other stuff we can do with SAM and show its capabilities, and then end with how we develop the delivery factors. So with SAM, you can determine pollutants of concern, identify critical locations and sources, and then develop and customize scenarios, and then run a bunch of analysis on those scenarios. Here's an example of just kind of plotting. You can plot concentrations, loading rates, do duration curves, pie charts. Has a lot of different things. You can also take results and map them spatially. So when we did our SAM training last year, this is an example from that where we can plot or just quickly map the TN loading rate by subwatershed. And then being able to customize a scenario, we can look at different land use changes, different types of BMP implementation. SAM has kind of a database of a lot of different BMPs. And then you can customize that BMP. You can set a cost and a participation level. And you can even edit the efficiencies in that database if you have a better information in your watershed. You can also do point source alternative scenarios. You can cap certain concentrations or scale means, even add a new facility if you have a new one coming online. Then you basically add all these designs to a scenario, and you have an option to also include climate change. It's pretty simplistic, that's currently built in, but once you run that scenario, you can do a lot of different types of analysis. This is, again, from our training that we did, kind of showing the percent reduction from this certain scenario. And then it also has the ability to optimize scenarios. So you kind of prioritize your subbasins that you're looking at, target different BMPs, and then you can set optimization targets. So like say you want a 10% reduction in TN or TP, you can set that target, and then it kind of goes through an optimization to find the best set of BMPs in the best spots, and then do some more analysis to see and actually run the model to see if those work and gets you to your target. So delivery factors, use the model years 2004 to 2022. And the first step is to export our local loads from SAM. And these are the local loads delivered to the nearest stream. So your unique source and your unique sub-watershed. Then we also export the transported loads or fate loads. And these are the loads delivered to a selected outlet. So like your local loads would be up here, and then the loads delivered to your outlet would be down here. So what actually makes it to your outlet? And it's estimated through calculations that track loss and resuspension from upstream to downstream. So it includes all of the things that HSPF simulates. So settling, scour, nutrient consumption, algae growth and death. And then we have our resuspension loads, which is the minimum of our daily net scour or available deposited amount multiplied by the resuspension rate. So this rate is kind of the main assumption in this whole process. And it's 0.5 for this, which is pretty standard. So that means half of the scour load is available from the previous deposition. And then to get our delivery factors, you basically take this transported load divided by your local load to get your factor. So here's the results, just shown spatially for nitrogen. And results make sense where you have lower factors, and then as it moves down through the watershed, you're getting more of those losses occurring. And then if you start here, you'd expect those to be a little higher because your outlets a lot closer. And here's phosphorus showing pretty much the same trend. And then finally sediment. Sediment looks a little bit different, and this is primarily due to you have different areas with higher scour occurring. So more of that load makes it to the outlet. So now I think I'll pass it back to Tam. They're going to go through the next steps.
Yes, thank you. And we will get to questions, I promise. We just sort of wanted to kind of tie things together back to the legislation and the requirement of this to develop transport zones and delivery factors. Thank you, Chris. That was, it's a lot. It's a lot of information. And I expect a lot of people are kind of like, I need to think about this for a minute.
Yeah.
We will be posting this presentation to the website. And we are opening a stakeholder review process. The report is posted to the website already. And that is, the link is provided in the agenda that was attached to the meeting invite. If you want the model itself, you can email me directly and I will get you those files. We do have a limited amount of funding. I will say that the Lower Neuse Basin Association did request to have a consultant provide some preliminary review throughout the development of the model. And they did provide some some preliminary comments on the hydrology review and the water quality calibrations, and we appreciated that. It was, it's hard to do when funding isn't built into it, and so we're doing this as a separate process. And it does need a quick turnaround. So we will ask for comments to be submitted by April 1st, and those comments can come directly to me as well. I did want to talk a little bit more about transport factors and the delivery factors. And John Heisman has prepared a quick comparison, just looking at the original transport factors and or zones and what is being predicted now by the model. So John, if you want to share your screen and show that.
Sure. Let me just do that. Yeah. How's that looking?
I mean, I could see it, and I have terrible vision.
Okay. Yeah, great. So again, everybody, I'm John Heisman, and I work with Pam and DWR, but I work in the non-point source planning branch where we implement the nutrient management strategy rules. And what I wanted to show you here is I put together this draft table that looks at what the current transport factors that are used under the Neuse implementation, and just compared to the numbers I pulled from the respec report. And just want to like kind of caveat all this, like this is a draft table. These numbers are all under review. These aren't final numbers, but I just thought it would be helpful to take a rough cut look at the differences and similarities in what the numbers we're currently using versus the numbers under review in the report that respec is provided. And the way I organized this table was, as Chris was talking out, they have those 231 watersheds, sub-watersheds from the model, and there's one receiving reach within each watershed. So that first column is the reach ID that's provided in the report. The second is the description of the reach, where the different receiving reach, the name of that reach. And then to kind of help orient you, like I listed the 27, 28 different Neuse River Compliance Association facilities that are located within each of those reaches and their associated permit. And this column here are the current transport factors that are used on the implementation of the rules, where we have these different transport zones of 10%, 50%, 70%, and 100%. And this is all like basically working from the top of the river basin down towards the estuary. And to help compare, I provided the nitrogen transport factors from the respec report that are under review, and the difference between the current and the ones in the report. And I did want to highlight that I also included the transport factors from the report using the full 3 significant figures that they provide in the report for the purpose of the comparison, just to make it easier to look at these numbers side by side. I've done it with 1 significant figure because we have to think through whether it's even appropriate that how many significant figures we would use here. But just since we currently have 1 significant figure, I thought it would be helpful to compare using 1 significant figure. And as you can see, it's pretty interesting. The people that came up with the original transport factors did a pretty good job. You can see that things are pretty close. We don't have like huge differences. Things are lining up pretty well with some minor variations as you work down the basin, but we're not too far off on what we're currently using. But I also want to highlight, like, the way I did this color coding was the grays, the 10% for the current, green is the 50%, blue 70, and the purple's at 100% reaching the estuary. And for these 3 that are in the gray, these are all to be determined still, because as you know, these 3 facilities are located above Falls Dam, up in the Falls watershed. There's different transport factor things going on in terms of what is reaching the Falls Lake from these facilities, then what's happening in Falls Lake, and then what's being discharged from below the dam. So that's all things that we're going to have discussions with the Upper Neuse River Basin Association, the modeling work that they've done, and see if there's any additional tweaking that needs to be done to kind of have this all fit together. But I just thought it was useful to look at these side by side. You know, the 50% transport zone, you can see the estimated numbers from the report range, you know, from 3 to 4 to 5 to 7. So like, you know, kind of as you're working down, like nothing huge difference. Several are pretty spot on in terms of comparison, the current to the projected. You know, we'll take a look at a few things where there's some lower numbers, but see what's going on there. And I think maybe, you know, again, these are the numbers from the tables in the report. Haven't run like the SAM tool to look at the specific facilities and see if things kind of adjust based on running different scenarios. Again, working down the basin, in the 70% transport zone, the estimated nitrogen results were around 60 and 80% transport, and similarly getting down to that final transport zone of 100%, things were looking pretty close to 100%. So just some minor differences there. Again, this last column shows the full, you know, 3 significant figures for the results, and I did also include the phosphorus transport factors, just so you can see how those compare to the nitrogen transport factors. And by and large, they seem like they're a little bit higher for the phosphorus compared to the nitrogen. But anyway, I'll make sure, Pam, that I provide these slides that we can put this up on the website as well. And I'm happy to share this in email if people want to look at this kind of side-by-side comparison. I thought it was useful, but again, want to put that caveat out there that this is all under review. This is just kind of a tool to kind of compare the results in the report that are under review to what we're currently using and see just how different they were. You've already kind of covered this, but I just want to reiterate the obviously the report's on the website. Files are available upon request. The comments, you know, requesting those by April 1st. And I just want to make that additional point. You know, obviously, you know, technical comments on the report and the model are appreciated. But you know, just wanted to highlight the fact that all this work that has been done was not initiated by DWR. It all came from that legislation that was initiated through Stakeholder seeking legislation calling for this work to be done. So we also want to hear back, or I specifically want to hear back in the comments from stakeholders, their feedback on how we use this information and when these results are used through either future rulemaking or adjusting the strategy or through policy development or permits. So like just reiterating that DWR is doing this process to follow the legislation, but it came from stakeholder interest. So along those lines, we're very interested in hearing from you and your comments about how we use this information, or at what point we use this information going forward. So that'll be very helpful to hear back from you all concerning that. And I just wanted to put in here the project website in case people want to click through it through the presentation that's posted. And again, just put our contact information here. But with that, Pam, I'll kind of stop there and stop sharing my screen, and happy to help answer any questions about that table or any next steps.
Yeah, I will. Thank you, John. And I appreciate the comment too about, you know, we're also looking for feedback from the stakeholders on recommendations for the use of the tool. That's a really good point. I'm going to try to facilitate questions. So I guess if you can raise your hand and I'll try to catch it as it goes. If you have a question for either for Chris and the Respect team or for DWR staff members as well. Go ahead and let her rip.
Everybody's happy.
Right. Okay, here we go. Barrett Jenkins.
Hey, yeah, I guess just from your level of experience, you know, how conclusive is like the data set that you used? How do you feel and using this model to change legislation that's been in place 20 years. And like, how complete is your data set? I like the model functions as intended, but like you mentioned a couple of times, you don't have necessarily complete data or multiple data sources for a lot of the significant inputs. And I'm sure you're obviously that's very difficult to get, and you're limited that way a lot of times. So I just wanted to know from y'all's perspective how like robust and defensible this model's projection is.
Yeah, I appreciate that question. I would say for some of the parameters where we had less data, it was sort of because the model can do it, we included it, but they were less of the focus of this effort. We do have really good data sets. We were lucky, given an unfunded legislative mandate, that we did have quite a substantial, robust record for nutrient data collection in this Neuse watershed. And also good point source data as well. So we feel pretty comfortable that the data available supported the defensibility of this effort.
I guess just for a specific follow-up, we've had through the history of North Carolina sort of agricultural non-point runoff from land application of animal waste is not really regulated or monitored that closely. So how does that input play into the model, since arguably there's not really accurate data to put that in? And there have been some newspaper articles about how large that impact might be.
Yeah, so I can take that, Pam. We estimated it, Chesapeake the Chesapeake Bay. They had a ton of money to do a lot of different stuff. So we basically used an algorithm that they used in their big modeling effort to estimate kind of the breakdown of, the manured areas versus unmanured. And maybe Cindy remembers, but I think it was a function of the animal units in the watershed and the amount of grain or something like that. But so yeah, that's, an estimate. We assume that it is happening, and just to be able to kind of use that assumption and model that. But
yeah, it'd just be interesting to get that data if it's available on the assumptions used there. Thank you.
Mm-hmm.
Thanks. Dan McLaughlin.
Thanks, Pam. Nice to see you again. I had a couple of questions, and one is, I think I understand how this information applies to the point sources. I don't understand how the information will be used for nutrient credit projects. Is that something that's discussed? Yeah, I didn't see that as I hastened through the materials today. So I don't have an understanding of how that would apply.
Hey, Dan, Pam, this is John. It's okay if I address it.
Sure.
So, yeah, I mean, so as you know, like right now, the idea is like you have point sources located in various points throughout the watershed, and then they have the option of purchasing nutrient offsets to offset discharges, and those projects can be located somewhere else. So we need transport factors, and we have those current transport factors that are applied to credits that you're purchasing that are located outside of the transport zone that the facility is located in. So I mean that the idea is to apply the transport factors to the credit that you're purchasing based on where it's geographically located within the watershed. I mean that's what's currently being done with the current transport zones. And then the idea here is having, more refined numbers through this modeling effort that go beyond those 4 transport zones at 10%, 50%, 70, and 100%.
So for example, if you have purchased nutrient credits that are in a 70% zone, but you're in a 50% zone, then you're going to get extra value for those credits, so to speak? Because they're further downstream.
I mean, that's you're getting the value of those credits based on where they're located. So yeah, I mean that the way that math would compute is you're getting those credits based on that 70% transport zone that they're located in. So it just provides the flexibility of calculating based on the true geographic location of where those credits are being generated and the impact to the estuary, versus like in the past, I think point sources were limited to like offsetting, buying credits that were located within the same transport zone, but this provides that flexibility at looking in areas outside the transport zone and applying the appropriate transport zone credit.
Thanks. I have a couple of minor things on your chart.
Sure.
I don't think that Little Contentnia Creek is down in Craven County. And so that's shown as the creek into which the Marine Corps Air Station, Havelock, and Craven County are discharging. I know that Marine Corps Air Station and Havelock discharge into Slocum Creek.
I'll take a look at that, because I was updating, and I appreciate you pointing that out. I was updating the table this morning, and it caught my eye, but I didn't have a chance to triple check that. But as I said, consider this a very draft table. I may have made some human error when I was transposing things, but I'll definitely go back and look at the report, look at what if I had transposed something incorrectly, or look at if there's a correction that's needed in a table in the report. But thanks for pointing that out.
And it appears to me that Fuquay is not on there at all. So as a discharger, Fuquay should be on there.
Yeah, I may have missed that. I was going off of my list.
Just point those out.
Yeah, thanks.
And one more quickie, maybe a quickie. Wetlands definition for the modelers. Obviously, there's been lots of national debate for a long time now, intensely for the past 7 or 8 years, about what are wetlands. How are wetlands used and defined for purposes of land cover designation in this information?
Yeah, for wetlands, we just use the NLCD 2019. I think they had like woody wetlands and whatever the other one is. So that class basically just carried over, and then using work that's been done before, knowing that loading rates of sediment and other things are usually quite lower in those areas. That's how we parameterized it. So.
All right, thanks.
Yep.
Okay, Deanna, you've had your hand up. Deanna Oshman.
I'll take it down now, thanks.
Yeah, thank you. So Pam, I'm going to be sending you a series of questions to help me understand better. You're right, this is a lot of material, and I tried reading the report in advance, but to help me put together this list of questions, I have a few things I'd like to ask about. The first thing is bouncing off the first person's questions around manure from the Chesapeake Bay. So a lot of the manure in the Chesapeake Bay is either dairy cows, which we don't really have any of, or it's poultry litter. And we have poultry litter in the Neuse, but we also have hogs. So my question is, how do you take those types of manure and put it into our systems? Excuse me. So that was one concern. The second concern I have is that there was a statement in the report that said that they used manure rates to determine fertilizer rates, and that's something we would never do. And then the third thing is that we have real specific rates of application in North Carolina, and it seems like those weren't considered. So I hopefully those three questions can be tied together.
I don't know, Cindy, if you're still on. You did a lot of that upfront calculation stuff.
Yeah, I would have to look. It's been a long time since I've looked at it, but I do believe we had the main feedlot numbers. And then because a lot of that is only the swine and cattle, then we use the egg census to try to estimate chickens as well. And then like Chris had said, there's an equation that we used from the Chesapeake Bay that kind of just transferred the grain, or corn essentially. Different types of corn is like what they mean by grain, I think. But those acres, and using the numbers that we had by sub-watershed to estimate the manure applied. So we had used a couple different sets of numbers and tried to evaluate which one was the best.
So how did you use manure for fertilizer decision making?
I might put this back to Chris, but I believe when it comes down to like manure application in the model, it's not necessarily like an explicit application of manure. It's more kind of calibrated when you're looking at watersheds that have a large amount of the manured grain versus unmanured grain. You're gonna tease a little bit of that out with the calibration itself, if that makes sense. And they're just gonna have different components. So it's really rough. You're looking at pretty large areas, and that percentage wise of what's manured versus what the crops are getting, if it's inorganic, are just going to be teased out, some of it in the calibration itself. Lupo, is that correct?
Yeah, they basically give us like a starting point for calibration. And really, like all the egg is set pretty much the same. We just have a kind of a higher organic component if it's manure. And then yeah, those don't stay the same, but they kind of adjust together up and down based on what we're seeing with the in-stream results and loading rates.
Okay, so it's tied back to the water quality.
Yeah.
This is Seth. I'll jump in real quick. So I think the Chesapeake Bay equations, even though they may have a dominant, animal type, in their equations, they do have, a big range of animals that they consider and what nutrients they contribute. So I think they definitely have swine in there in those calculations. But in general, we use the animal units in that equation to estimate the area that's manure fertilizer. And then, based on crop types and those, sort of practices, any other areas that are assumed to have fertilizer as well are just assumed to have chemical fertilizer. So really the animal units didn't themselves determine, which areas are fertilized. It's really the crop type determined fertilizer, and then based on, the animal counts and the Chesapeake Bay equations, those kind of helped us separate which ones are manure fertilizer, which ones are chemical fertilizer, because those definitely do have different responses as far as water quality loads.
Okay, thank you very much.
All right. Thank you for those questions. Haywood?
To Havelock and Marine Corps Air Station, both of those facilities built effluent lines that discharge, I don't know, half a mile, quarter of a mile out in the estuary. That was done 5, maybe 7 years ago. So there are no discharges in Slocum Creek now. And I don't know who to ask this question to, but or statement. It's in reviewing the report, my interpretation is that the point sources are delivering approximately 8% of the total nitrogen load to the estuary. Is that correct?
Oh, sorry. The source allocation, that's just to a local reach. So to get the actual amount that makes it to like the estuary, then that's when you have to do the transport or delivery factor to see what fraction of that gets there. But so that 8% is just kind of locally. Let's set it. Yeah, locally, that's what gets from its current sub-watershed to its current reach. But
So no one has calculated collectively what all the point sources are delivering using these factors to the estuary?
We can do that with SAM, and we have other tables of those things parsed out. So that was kind of a product that we delivered, was the SAM package, to be able to get at kind of those more detailed calculations.
Yeah, with the SAM, you can actually pick any point in the watershed and get the delivery factor from any source in any basin and their contribution to that, or the fate or transport factors to that point. So, I mean, for the overall transport factors that John was showing, those use the outlet or um, the lowest point in the watershed, where you could pick different points and get transport factors all the way up and get, the contribution from all point sources to at any point in the watershed. And you can tabulate those point sources and include them all as one output, or you can keep them separate and get the amount of contribution that each individual point source gets to any place in the watershed with the SAM application.
Okay, with the chart you have on the screen indicates the point source is greater than 500,000 a day to be 3.1%. Where is that 3.1% located? What is that a measure of?
That's across the whole watershed. So this is basically total discharge collectively across the entire Neuse River Basin. That's what is locally being delivered to its local reach.
Okay, thank you.
Yep.
So those are, that's a good question, Haywood. And, again, the focus of this effort was on transport factors. So if there's interest in sort of a holistic look at, total contribution of point sources, to the estuary, things like that, we're still learning the tools and we're still reviewing everything ourselves. So definitely next steps for us as we move forward here. Let's see. I think Ann Cohn, you have your hand up.
Yes, this is Ann Cohen. I had a couple of questions. Your boundary condition for Falls Lake, you utilized the nutrients, sediment, and stuff delivered from Falls Lake, but you didn't include the land use categories in Falls Lake. Is that correct?
Yes, that's correct. It's just, from that point from Falls Lake, that's the flow and the load that's coming into the model.
So what that means is, for example, in agriculture, you would have way underestimated the amount of pasture land contributing to the total model.
So this is the model domain. So you have to remember the watershed that is part of this particular model. And we didn't want to, because the Upper Neuse River Basin Association had put so much money and time into developing some pretty advanced modeling tools for the Falls Lake watershed and lake itself. It is sort of a combination of tools that need to be considered for a holistic look at the entire watershed itself.
Yeah, I understand that. I'm
Yeah.
just pointing out that is a pretty serious limitation from our perspective. And the other question I had was, does the model, not the SAM, but the model, does it include any best management practices or no-till farming or, I mean, a lot of it looks almost like it's bare ground. And I mean, even not including the crops, I'm trying to figure out what exactly I'm looking at. Are there any BMPs included? And the second question is the ground cover of the crops while they're on the ground included?
Yeah, so for the first question, I mean, they're kind of implicitly calibrated based on the in-stream water quality. So if we have areas where there's a lot of cropland, but not a really high load, then those are probably kind of implicitly represented in the model. And then to your second question, what was that again?
How did you look at land, like cropland is for your precipitation and runoff? Does it include the presence of the crops or not?
Yes, it does. Kind of like average, there's a lot of crop rotation that goes on year to year. We're kind of looking at it like overall, what is the average condition? It could be soybeans one year and corn the next, but we're kind of looking at the average condition, but those are represented by sub-watershed.
I noticed in your document you said that there is a great deal of variability in agricultural coefficients, runoff coefficients. And you're saying you started with the Chesapeake Bay coefficients?
We didn't start with those. We kind of parameterized it using past modeling efforts, kind of north of North Carolina, but and then a lot of it is just calibration. So we get a starting point, and we don't try to hit the Chesapeake Bay results. We just kind of use them as a tool to see, once we calibrate, it's like, yeah, we're showing the same trends like on a land use basis as what they're showing. So that gives us a little more confidence in our calibration.
So a lot of the variation, within a particular category that, we get from literature or from other areas, a lot of the differences are typically based on practices and things that aren't necessarily measured or we don't have data for. So it definitely helps to have a lot of in-stream data to look at, and those loading rates are calibrated based on what we see in the streams in different areas. So that's definitely the biggest reason why there's variation, is because there's a lot of stuff going on that's not really measured, or you don't really have data to represent. Like in the Chesapeake Bay, they do have a pretty extensive, detailed BMP tracking system, but that data wasn't necessarily available for this area. So we had to make some assumptions and calibrate those loading rates, assuming there's maybe some elevated, maybe more BMP here and here, but we didn't really have the data to support, a built-in, variation on that level.
I would have to say that would make a big difference in agriculture as to what BMPs and buffers and such were in place, being considered, because these concentrations are higher than what the literature here in North Carolina shows for agriculture.
Any other questions? I think we're just about at time. So I will, again, reviews open. We're looking for your comments. They can be sent directly to me by April 1st, please. And if you need I suspect most people would prefer to just review the report, but if you would like the model itself and have HSPF experience, let me know and I can get you those modeling files as well. I want to thank Respect for, this is a huge watershed and it's been a pretty heavy lift to develop all of this, including the post-processing, the SAM tool, which we're very excited to have. It's really going to make our jobs a lot easier moving forward. So I appreciate everyone's time today and throughout this process, all these stakeholder meetings and let's see, anything else? Look forward to working with everyone in the future. So I think with that, we can go ahead and end the meeting. But thank you, everyone.
Yeah, thank you.
Thanks, guys.
Thanks, everybody.